Uh, the next speaker is Peter Hazard from the University of São Paulo, and he's going to talk about the renormalization of Renorm-like mappings of bounded type.
Hello, can you all hear me? Okay. First of all, I'd like to thank the organizers for letting me talk. They say imitation is the sincerest form of flattery. So basically what I'm going to do is imitate some work by Welington and Alberto, if he's here, from 99, more or less. And using their ideas, we're going to bump this up to some statement for Renorm-like maps. What we've seen so far with a lot of talks is that there's a situation which we know, which is analytic unimodal, say, and we have a good renormalization picture for that. And what Welington has been fundamental in is being able to extend that to CK spaces for some K, basically using these ideas of embedding the space that you know something for and looking at the extension in an appropriate way. Okay, so the case that Alberto and Welington looked at was basically, so they took the space I to n b, which is the space of infinitely renormalizable let me just say unimodal maps C2 normalized. I won't say what that means, but and with nonlinearity bounded by B. Oh, and of bounded type, so of combinatorial type bounded by n. Combinatorial type. Well, let's say renormalization type. Bounded by n. Okay? And so their theorem well, in their paper it's stated as a lemma, but for me it's going to be a theorem. So, because they actually used this to prove a rigidity statement. But I'm not going to, for Renorm, we don't really have the same apparatus to make rigidity statements. So I'm just going to look at the lemma, which I thought was more fundamental. So, so let's state it. So for all n and b as above, let's say there exists, so now I need some numbers. So there exists a positive lambda less than 1, some mu, some c, such that the following holds. So if we take a map in this space, then there exists a sequence of quadratic-like, so I should say what this space is. This is the space of quadratic-like maps where the modulus is greater than or equal to this number mu, okay, such that the following two properties hold. So first of all, such that. First of all, the combinatorial type of the nth renormalization of f is equal to the combinatorial type. Yeah, no, let me write it like this. So combinatorial type of this Fn, and secondly, that if we look at the C0 distance between the nth renormalization and this quadratic-like map, then this is bounded by some constant multiple of lambda to the n. So the distances decrease exponentially. Okay, so far so good. So now okay, so let's remind ourselves of, okay, I need a little explanation of what combinatorial type is, I guess, although everyone in the audience knows already. So, but there is a distinction to be made. So combinatorial type just means the ordering of the critical orbit, at least in Welington's paper. And that's somehow analogous to renormalization type, where you have the decompositions of, if it's once renormalizable, then you have a unimodal permutation, which describes the first level of renormalization, and then second renormalization, you do the same thing. So I will abuse terminology a little bit and use the two terms interchangeably. Although when I say combinatorial type, I really mean renormalization types, okay? Right, okay, so let's remind ourselves more precisely with an example of what a unimodal permutation is, or what a unimodal renormalization type is. So we take a map and we take the interval and we fold it unimodally, and then let's say we have three intervals, J0, J1, and J2. Then the unimodal map is going to map J0 to J1, and then it's going to map the interval J1 into J2, and then it maps J2 into J3, and when you return, you come back as a unimodal map. Okay, so everyone is happy with this. Okay, so given any unimodal permutation of this type, we have a renormalization operator. Okay. Now, so now what we're going to do is move into 2 dimensions. So now I'm going to erase your theorem, Welington, I'm afraid. So, okay, so the maps I'm going to be interested in, well, the space of maps I'm going to be interested in is going to be this space, which I'll call H omega. B epsilon bar. Okay, and so the omega you don't really need to worry about. These are to do with complex extensions to some bidisk, so maybe let's ignore that for the moment. But what we're going to do is we're not looking at C2 things, we're just looking at analytic things with appropriate extensions. Okay, so we're going to look at maps of the following form, F, which send points x and y to some unimodal guy, F, minus some small epsilon perturbation, and then in the second coordinate, you get the old x coordinate. Okay, where F is unimodal, analytic, and epsilon, let's say we take the C0 norm on this little bidisk, and this is going to be bounded by epsilon bar. Oh, and I should say that the nonlinearity, so the nonlinearity of F is bounded by B. Okay? Okay. So, let me not get into this, but this is just basically the same thing as you do in one dimension. Okay. Well, it is a one-dimensional statement. Okay, right, so these guys take, so everyone knows what these guys do, right? So you start off with a little box, the interval cross itself, say, and then what this guy is going to do is map this box into sort of, so it's going to map these horizontal lines with a unimodal looking thing. So its image will look something like this. And the important thing is that these horizontal lines get mapped to these vertical lines, get mapped to horizontal lines. Okay, so this is the image of F. Okay, so we have, okay. Right, so if we take very small epsilons here, so the epsilon bar is really tiny, then we essentially have something which should look like a unimodal map. Okay. So we're going to try and build, for these maps, something which looks the same as unimodal renormalization. Okay. So I'm going to draw the following cartoon. Right. So before I draw a cartoon, I'll give the definition, but the cartoon afterwards will describe what's going on. Okay, so this is a sort of topological definition, and then there's sort of an analytic part which you can build into this later, which is to do with changes of coordinates. Because when you renormalize, when you look at a higher iterative one of these maps, it's not of the same type. It doesn't map the second coordinate. X isn't the second coordinate necessarily. So you need a change of coordinates, but modulo this change of coordinates, the renormalization operator will be the following thing. Okay, so we take a closed topological disk, and we're going to take some fixed non-flip saddle point and some non-flip period p saddle of some period. And then, okay. And then I have another p, which isn't the first p, but I think you'll understand that these things aren't the same. So we have a p and a q, which lie in the intersection of the unstable manifold of our non-flip saddle and the local stable manifolds of one of these points in my periodic orbit. Okay? And I impose the condition that these 2 points have to lie on opposite sides of the stable manifold. And this is some sort of non-intersection condition. So I should describe this notation. So if I have a point, 2 points, P0 and Q0, lying in the unstable manifold of a point, the interval between them with this U just means it's the unstable arc in this unstable manifold between the points P0 and Q0. Okay, so ignore this technical condition because I'll show you the picture in a second which explains what's going on. Okay, so under this, with these technical conditions here, you can say that F is renormalizable. Okay. Why can we say it's renormalizable? When it's renormalizable, you want a disk which somehow maps back to itself under some return. Okay, so if we take the stable arc between these 2 intersection points and the unstable arc between the same 2 intersection points, then these guys will bound a domain. And when you look at the iterate of this domain, under the pth return, this guy will map inside itself. Okay? And we call this guy the renormalization domain. Or, to be a bit more precise, I will call it the topological renormalization domain, because with this change of coordinates, there's something else going on which I'm not telling you about. Okay? So the picture is, okay, so this is what I've already said. So these conditions basically ensure this property. Okay, so the picture is the following. Let's go back to this period 3. Okay, so we have our beta naught fixed point here, this saddle, and then, okay, this is some other saddle point over here, but the thing that I'm interested in is is this period 3 cycle here. So this guy goes to this guy, goes to this guy. And as I said, epsilon is small, so if we choose epsilon small enough, these local stable manifolds are basically straight lines. Okay? And so let's see what happens when we continue the unstable manifold of beta naught. Okay, so this guy is going to go along, and then it hits at some point P naught, and then it comes around and it hits this, this local stable manifold at this Q naught, and this is going to be, this blue region is the renormalization domain. So just to try, hopefully convince you, so you look at the iterate of this guy, and it's going to map to some domain over here, because this point goes to this point. So there's going to be a point over here which maps to this point here, and this point will go somewhere over here. And then you do the same thing again, and you get something which looks like this. Okay? And then you do the same thing again, and this guy winds all the way around, and then eventually you land back inside your original renormalization domain. Okay. Now, when talking about bounded type, it's nice to have two examples of these things, okay? So I'll give you another example. Okay, so now a little more complicated, period 5. The reason for this guy is important later if I get to speaking about, which I won't, to getting to speaking about unbounded type. But so this guy is just a guy with 5 intervals. This guy goes here, goes there, goes there, goes there, goes there, okay? And then, just because I want to show you the picture, you have the same thing going on again. So you have some point over here which I haven't drawn, this flip saddle. It goes around, intersects, comes around, and then you do the same yoga. You just follow these guys around, and then eventually you land back, okay? And trust me, these are one of the easier pictures to draw, okay? So, okay, so I basically have 5 minutes. So, so what I should do is, okay, so now I'm going to write state the theorem. So theorem. Okay, so for all n and beta, and let's say b is sufficiently large, let's say, just to get rid of non-trivial cases. Okay, then there exists numbers like this, and there exists a c and an epsilon bar, such that the following holds. So first of all, somewhat trivial statement, well, the easiest statement. So, I didn't say what, I didn't introduce some notation. So we had a curly I, which was the space of all infinitely renormalizable maps for the unimodal. I'm going to use this notation to denote the space of all infinitely renormalizable Henon maps of bounded type with this B. But now we have this extra parameter epsilon bar, which controls the thickening for the renormalization. Okay? So this is just the space of infinitely renormalizable guys of bounded type that I'm looking at. Okay? Then, obviously, although it's a little bit of work, so this coincides with the stable manifold of the renormalization. Well, yeah, let me say the renormalization operator, although it's really more of a semi-group. So this is going to be the stable manifold of the limit set of the unimodal renormalization operator of bounded type bounded by n, right? Appropriately intersected with this space of Henon-like maps. Okay. Okay, so this really what this is saying is that the space of infinitely renormalizable maps is the stable manifold. Part two is part parts 1 and 2 were basically hyperbolicity statements. So if we take two infinitely renormalizable guys, and okay, let me use this notation. So upsilon f is equal to upsilon g means that, i.e. combinatorial renormalization type of the nth renormalization of f is equal to the renormalization type of the nth renormalization of G for all n. Okay, that's what I mean by this notation. Upsilon is the space of all unimodal permutations associated with all renormalizations. Okay, then this is bounded by some constant multiple times this lambda, so you get this exponential contraction. And then the second part is if they're not the same. So basically you have hyperbolicity. Okay, so that implies that Rn of f minus Rn of G is going to be greater than or equal to C times this mu n for all n less than or equal to some n naught dependent on the combinatorics. Okay, so that's the main theorem that I wanted to state. And the idea is, I mean, it's some work, but it's basically in 2 minutes. Let me explain really what you're trying to do and where Welington's theorem comes in. Okay, so you have your space of so you have your space of Henon-like maps here, and you're going to have, let's say you have some domain of renormalizability for tripling, and you have some domain over here for this period 5 I told you about, okay? And so the first step is, okay, so let's say they're of the same, so you take a map, this map F and this map G, and you know that the epsilon part shrinks super exponentially. And what you can show using Welington's result is that actually, okay, so what you can do is project. Each time you renormalize, you can project these guys into the unimodals. The problem is that the projection isn't necessarily infinitely renormalizable. Okay? So, but we know that it's very close to something which is infinitely renormalizable. So with Welington's result, what you can do is you can project it into something which you'd imagine was the space of maps with the same combinatorial type. Okay? So this gives you, now I've run out of too few dimensions, but you have an f and a g. You have a little f and a little g, which you project to. And with Welington's result, you can control the iterates. So this gives you a sequences of f and g's, which, so this isn't a sequence of renormalizations, but then you shadow this sequence of f and g's with an appropriate shadowing lemma. And then once you have an actual orbit which shadows these f's and g's, by the hyperbolicity in dimension 1, you know that you get exponential contraction, say. And in the first case anyway, you get exponential contraction. And these guys, your actual approximations, are also exponentially close. And these guys are also super exponentially close here. So you get exponentially close, okay, under the sequence of renormalizations. Okay, so that's the idea of the proof, but I don't have time to go into details. I have some more minutes. Okay. Okay, then. Okay, what I can do is either. No, okay, let me give a few more details then. Let me be a bit more precise. So first of all, it's probably better to draw a three-dimensional picture. That'll make it clearer. Okay. So this is your space of unimodal maps, and so let's say you start off with, so let Fn equal the nth renormalization of F, and Gn equal the nth renormalization of G. Okay. And with Welington's result, we can take an Fn, which is going to be the projection to the same combinatorial class as the Fn of, by combinatorial class, I'm saying it has the same types of renormalizations at each renormalization step. Okay, so of Fn, and we have the same thing for Gn. Okay, right. So what Welington's result plus this super exponential contraction gives you is that, okay, so you have an Fn here, and first of all, you can project this in a canonical way into an arbitrary unimodal map. And if this distance is small, so your epsilon is small, and this guy is many times renormalizable, is infinitely renormalizable, then when you project, you'll get something which is like 1,000 times renormalizable, okay? And the number of times that you're renormalizable will grow as this distance shrinks, okay? So this gives you some. So I've already labeled the Fn's and Gn's here, but this is what, let's call this F hat N, okay? So you have some unimodal map by a standard projection, and then by Welington's result, you can project this actually to a bona fide map of the given renormalization type that you're interested in, okay? So this is, so this is F. So this is this map, Fn, okay? And by Welington's result, you know that this is going to be exponentially small, okay? And we know that this is super exponentially small, so this distance here is exponentially small. Okay. Right, so, but we're not quite done yet. So all we have at the moment is a sequence of points which get exponentially close to the points which we're actually interested in. Now, if these guys were an actual orbit, we'd be done because of Mishra's result, hyperbolicity of renormalization for unimodal maps, and for bounded type. You'd contract exponentially quickly, and then by the triangle inequality, you'd be done, right? So, but that's not quite good enough yet because this thing isn't an actual, isn't an orbit. But you can show it's a pseudo-orbit of a certain type. And in fact, it's a pseudo-orbit where the distance between the image under renormalization and the next Fn grows exponentially small. So it's better than a pseudo-orbit, okay? And then once you have that, you can use the argument which I said for the case when it was an actual orbit of renormalization, and you're basically done. Okay? And now I think I am over, so I'll leave it there.